What if everything you think you know about reality is just one side of the story? Picture a world where time runs backward, where flames freeze into ice, where the past becomes the future, and the future rewinds into the past. This isn't just a scene from a science fiction novel, it's the startling premise of the cosmic mirror theory, a radical idea that turns our understanding of the universe inside out. For centuries, we've assumed time moves in one direction, that cause always comes before effect, that the laws of physics are fixed and unchanging. But what if our universe has a hidden twin, a parallel reality where all these rules are flipped? The cosmic mirror theory isn't just a wild thought experiment. It's grounded in some of the most advanced physics humanity has ever discovered. From the enigmatic behavior of antimatter to the eerie symmetries hidden in the equations of quantum mechanics, there are clues scattered throughout the cosmos that suggest our universe might not be alone. Imagine looking into a mirror and seeing not just your reflection, but an entire alternate reality staring back, one where entropy decreases instead of increases, where black holes might spew out matter instead of swallowing it, where the very fabric of space and time dances to a different tune. This isn't just about a parallel universe, it's about a universe that's fundamentally inverted, a cosmic counterpart playing by opposite rules. Today, we're going to take a journey into this mind-bending possibility, exploring what a backward universe could teach us about the deepest mysteries of existence. Why does time move forward in our world? What happened during the Big Bang that set this asymmetry into motion? Could dark energy, the mysterious force accelerating the expansion of our cosmos, have a mirror counterpart balancing it out? And if such a universe exists, how could we ever detect it? These aren't just abstract questions, they're puzzles that could redefine our place in the grand scheme of reality. So buckle up, because by the end of this exploration, you might never look at the cosmos or even your own reflection the same way again. The mirror is calling. Let's peer through it together. The cosmic mirror theory isn't just a fantastical idea plucked from the pages of speculative fiction. It's a serious scientific hypothesis with roots in some of the most well-tested principles of modern physics. At its core, this theory suggests that our universe might have a perfect counterpart, a twin reality where everything operates in reverse. Time flows backward, particles spin in the opposite direction, and even the fundamental forces could behave in mirror image. Think of it like a cosmic dance where every step we take forward is matched by an equal step backward in this hidden twin. But how could such a bizarre concept emerge from the rigorous world of physics? The answer lies in the delicate symmetries woven into the fabric of reality itself. One of the key pillars supporting this idea is CPT symmetry, a fundamental principle in quantum mechanics. CPT stands for charge, parity, and time, three fundamental properties of particles. The symmetry suggests that if you take a particle, flip its charge, mirror its spatial orientation, and reverse the flow of time, the laws of physics should remain unchanged. In other words, the universe should behave the same way under this radical transformation. The cosmic mirror theory takes this a step further, proposing that there might be an entire universe where CPT symmetry isn't just a mathematical quirk but the defining feature of reality. But why would physicists even entertain such an outlandish idea? It all comes down to solving some of the most perplexing mysteries in cosmology. Take the matter-antimatter imbalance, for example. According to our current understanding, the Big Bang should have produced equal amounts of matter and antimatter. Yet, our universe is overwhelmingly made of matter. Antimatter is vanishingly rare. If a mirror universe exists, it could help explain this discrepancy. Perhaps the antimatter didn't disappear, it simply went to the other side of the cosmic mirror. Then there's the enigma of dark energy, the mysterious force accelerating the expansion of our universe. Could it be that this expansion is balanced out by a contracting mirror universe, maintaining some grand cosmic equilibrium? Even the arrow of time, the one-way flow from past to future that we take for granted, might not be as absolute as it seems. In a mirrored reality, entropy could decrease instead of increase, creating a world where shattered glass reassembles itself and flames draw heat back into their source. Of course, this raises a host of mind-bending questions. If such a universe exists, how could we ever detect it? Would its inhabitants experience time in reverse, remembering the future and anticipating the past? And perhaps most intriguingly, could there be any interaction between our universe and its mirror twin? Some theories suggest that quantum entanglement, the phenomenon where particles remain mysteriously linked across vast distances, might hint at a deeper connection between these two realities. The cosmic mirror theory challenges us to rethink the very foundations of what we consider possible. It's not just about imagining a universe with different rules. It's about confronting the unsettling idea that our own reality might be just one half of a much larger, far stranger cosmic equation. As we peel back the layers of this theory, we're forced to ask, is the universe we see the only one, or is it merely the reflection of something far more extraordinary? Time reversal symmetry might sound like something straight out of a time travel movie, but it's actually a well-established concept in physics. At its heart, this idea suggests that the fundamental laws governing our universe don't actually care which direction time flows. They work just as well whether time moves forward or backward. Think of it like a film reel. If you watched a recording of two planets orbiting each other in reverse, the motion would still obey Newton's laws of gravity perfectly. The equations don't favor one direction over the other. This symmetry shows up everywhere, from the motion of planets to the collisions of subatomic particles. Even the equations of quantum mechanics, which describe the bizarre behavior of particles at the smallest scales, treat time as reversible in principle. Yet, if the laws of physics are so indifferent to time's direction, why does our everyday experience feel so one way? Why do we remember the past but not the future? Why does coffee always cool down instead of spontaneously reheating? The answer lies in a concept called entropy, often described as the measure of disorder in a system. The second law of thermodynamics tells us that entropy always increases over time, or at least it does in our universe. This relentless march toward disorder gives time its arrow, creating the familiar flow from past to future that we take for granted. But here's where things get really interesting. If entropy defines the direction of time in our universe, what would happen in a mirrored reality where entropy decreases? Imagine a world where shattered glass shards leap back together, where smoke funnels into a cigarette instead of dissipating, where heat flows from cold objects to hot ones. In such a universe, time's arrow would point backward from our perspective, yet it would feel just as natural to its inhabitants as our forward-flowing time feels to us. Their past would be our future and vice versa. This raises a profound question. Is time's direction truly fundamental, or is it just a local feature of our cosmic neighborhood? Some physicists speculate that the Big Bang might have set the initial conditions for our universe's low entropy state, effectively winding up the clock in one direction. If a mirror universe exists, its Big Bang could have done the opposite, creating a reality where time unfolds in reverse. The two universes would be like cosmic twins, born together yet evolving in perfect opposition. Of course, this doesn't mean we'll ever see time running backward in our own world. The sheer number of particles in even a simple object makes the odds of spontaneous entropy reversal astronomically low. But on the quantum scale, things get murkier. Some experiments suggest that certain particles, like neutrinos, might behave differently if time were reversed, hinting at subtle asymmetries in the fabric of reality. Could these tiny cracks in time's symmetry be echoes of a mirror universe tugging at the edges of our own? The answer might lie deeper in the mysteries of quantum mechanics and the strange, shimmering boundary where our universe meets its possible twin. Antimatter isn't just the stuff of science fiction, it's a very real, very puzzling component of our universe. At first glance, these particles seem almost identical to their ordinary matter counterparts, but with one crucial difference: their charges are flipped. Take the positron, for example. It has the same mass as an electron, but where an electron carries a negative charge, the positron shines with a positive one. This symmetry is so precise that when matter and antimatter meet, they annihilate each other in a burst of pure energy. It's as if nature built in a perfect undo button, allowing particles to cancel each other out completely. This mirror-like quality has led some physicists to wonder, could antimatter be more than just an exotic oddity? Could it actually be a window into a backward universe, where time flows in reverse and physical laws operate in perfect opposition to our own? The cosmic mirror theory takes this idea seriously, suggesting that antimatter might not just resemble a reflected version of matter. It might literally be matter from a mirrored cosmos leaking into our reality. Imagine dipping your hand into a still pond. The reflection you see isn't just an image, it's light from another world, distorted but real. Antimatter could be something like that, a tangible piece of an inverted universe brushing against our own. Yet here's the mystery that keeps scientists up at night. If the Big Bang produced equal amounts of matter and antimatter, why is our universe overwhelmingly made of ordinary matter? Where did all the antimatter go? One tantalizing possibility is that it didn't disappear. It simply ended up on the other side of the cosmic mirror. In this scenario, the Big Bang didn't just create our universe. It created two universes, one matter-dominated and the other antimatter-dominated, forever separated by some fundamental barrier. This idea gets even stranger when you consider that antimatter doesn't just have opposite charges, it also behaves slightly differently under certain conditions. Experiments at CERN have shown that some antimatter particles decay at rates that aren't perfectly symmetrical with their matter twins. These tiny asymmetries might be clues pointing toward a deeper connection between antimatter and time reversal. If antimatter truly belongs to a mirrored universe, these subtle differences could be the fingerprints of that other reality pressing against our own. Could there be entire regions of space where antimatter dominates, hidden from our telescopes? Some theories suggest that vast antimatter galaxies might exist, their stars shining with the same light as ours but built from positrons and antiprotons instead of electrons and protons. The challenge is that antimatter emits the same light as ordinary matter, making it nearly impossible to distinguish at cosmic distances. The only way to spot an antimatter star would be to catch the telltale gamma-ray flash of matter and antimatter annihilating at the boundary between the two realms, a boundary that, if it exists, remains frustratingly out of sight. What's truly mind-bending is the possibility that life could exist in an antimatter universe. If the physics is simply mirrored, then antimatter planets could have antimatter chemistry, antimatter biology, even antimatter civilizations. From their perspective, we'd be the exotic, backward ones. This raises profound questions about the nature of reality itself. Is our universe just one half of a grander cosmic duality? And if so, what does that say about the fundamental symmetries and asymmetries that shape existence? The scarcity of antimatter in our universe might not be a bug in the cosmic code but a feature, a clue pointing toward a much larger picture. Every time physicists create and study antimatter in labs, they're not just probing the edges of known physics. They might be peering through a crack in reality, catching fleeting glimpses of a world where everything we know is inverted. The more we learn about these mysterious particles, the more they seem to whisper secrets about the universe's hidden symmetries, and the possibility that we're living in just one reflection of a far stranger, far grander cosmic truth. CPT symmetry might sound like an abstract concept, but it's one of the most ironclad rules in all of physics. Imagine taking the universe and performing 3 radical transformations at once, flipping every particle's charge, creating a mirror image of all spatial coordinates, and reversing the flow of time. According to CPT symmetry, the universe should behave exactly the same way after this dramatic makeover. It's as if reality has a built-in balance, a cosmic checks and balances system ensuring that no single perspective is privileged over another. This symmetry isn't just a mathematical curiosity. It's been tested with extraordinary precision in particle accelerators, where the behavior of matter and antimatter confirms these mirror-like properties down to the tiniest fractions of a percent. The cosmic mirror theory takes this idea and runs with it, proposing that CPT symmetry isn't just a property of particles, it's the blueprint for an entire parallel universe. If our universe is the positive version with matter, right-handed spins and forward-flowing time, then its twin would be the ultimate negative image, antimatter, left-handed spins and time running backward. Think of it like a cosmic coin toss. When the Big Bang happened, it might not have produced just one universe but 2, each representing opposite sides of the same fundamental symmetry. What's truly fascinating is how this idea could solve some of cosmology's biggest headaches. Take the matter-antimatter imbalance, for instance. If the Big Bang created equal amounts of both, where did all the antimatter go? The mirror universe hypothesis offers an elegant answer. It didn't go anywhere. Instead, the antimatter ended up in the twin universe, separated from ours by some fundamental divide. This wouldn't just explain the missing antimatter, it would also preserve the perfect symmetry implied by CPT, just on a much grander scale. But the implications go even deeper. If CPT symmetry holds universally, then the mirror universe wouldn't just be a quirky alternate reality. It would be a necessary counterpart to our own, balancing the cosmic books. Every star in our sky might have an antimatter twin in the mirrored cosmos, every galaxy a counterpart spinning in the opposite direction. Even black holes, which devour matter in our universe, could have inverted twins white holes, spewing out material in the mirror world. The Big Bang itself takes on new dimensions in this framework. Instead of a single explosive origin, we might be looking at a dual birth, with 2 universes emerging back-to-back like cosmic phoenixes. Some theories suggest that the initial singularity could have split along the lines of CPT symmetry, creating 2 timelines that evolve in opposite directions. This wouldn't just be a matter of time running backward. It would mean that every law, every force, every quantum interaction in the mirror universe is the exact inverse of ours. Yet, for all its elegance, the theory raises as many questions as it answers. If the mirror universe exists, why can't we see it? How is the symmetry between the 2 realms maintained? And perhaps most intriguingly, could there be any interaction between them? Some physicists speculate that quantum entanglement, the mysterious link between particles across vast distances, might hint at a deeper connection, as if the 2 universes are whispering to each other through the fabric of spacetime. CPT symmetry doesn't just support the possibility of a mirror universe, it almost demands one. Without it, our understanding of physics would have an uncomfortable asymmetry, a lopsidedness that contradicts the elegant balance we observe everywhere else. The cosmic mirror theory isn't just about imagining another reality. It's about recognizing that our universe might be part of a larger, perfectly balanced whole, where every action here has an equal and opposite reaction in a world we've yet to fully comprehend. The moment of the Big Bang wasn't just the birth of our universe, it might have been the cosmic equivalent of a mirror shattering, sending fragments flying in opposite directions. Imagine the initial singularity not as a single point exploding outward, but as a fork in the road of reality, splitting into two universes with opposite arrows of time. This twin universe model suggests that what we call the Big Bang was actually a big reflection, creating two realities perfectly balanced yet inverted. In one, time flows forward as we experience it, with entropy increasing and stars burning fuel into light. In the other, time runs backward, with heat flowing from cold to hot and scattered particles spontaneously organizing into order. This idea could explain some of the most puzzling features of our cosmos. Take the cosmic microwave background, the faint glow left over from the early universe. It's astonishingly uniform, with temperature variations of less than 1 part in 100,000. Such uniformity is hard to reconcile with the chaotic frenzy of the Big Bang, unless there was something smoothing things out. A mirror universe could provide that missing piece. If the two universes were entangled at birth, their mutual influence might have acted like a cosmic iron, pressing out the wrinkles in space-time and leaving behind the remarkably even background we observe today. Then there's the mystery of missing particles. Certain theories, like supersymmetry, predict a zoo of undiscovered particles that should exist but haven't shown up in experiments. If a twin universe exists, those particles might not be missing at all. They could simply be hiding on the other side of the mirror. Just as antimatter seems scarce in our universe, these elusive particles might dominate the mirror world, balancing the cosmic scales in ways we're only beginning to grasp. But how would such a twin universe interact with ours? The answer might lie in the quantum realm. At the instant of the Big Bang, the two universes could have been quantum mechanically entangled, their fates intertwined no matter how far apart they've since expanded. This wouldn't mean we could send signals to our mirror twins. The laws of causality would still hold, but it might create subtle echoes between the two realms. Some physicists speculate that anomalies in particle physics experiments, like unexpected neutrino oscillations, could be faint ripples from the mirror universe brushing against our own. The implications of this model stretch even further when we consider black holes. In our universe, these gravitational monsters trap everything, even light. But in the mirror universe, their counterparts, white holes, could theoretically spew out matter and energy. If the two universes are connected through some higher dimensional bridge, black holes in our world might funnel matter into white holes in the mirror reality, creating a cosmic recycling system on an unimaginable scale. What's truly staggering is the possibility that the twin universe model doesn't just explain existing mysteries, it rewrites our understanding of the Big Bang itself. Instead of a singular event, we might be looking at a cosmic symmetry breaking, where the fundamental forces split not just into electromagnetism and the strong and weak nuclear forces, but into two entire universes with opposite properties. The energy of creation wouldn't have been lost, it would have been divided, with our universe getting one half and the mirror universe the other. This raises profound questions about the nature of existence. If the twin universe is real, does that mean every action here has an equal and opposite reaction there? Could the formation of a galaxy in our sky mean the dissolution of one in the mirror cosmos? And if time flows backward there, does that universe's Big Bang lie in its future, a destiny waiting to unfold? The answers might lie in the deepest laws of physics or just beyond the edge of our current understanding, in a mirrored reality we've yet to fully perceive. Dark energy is one of the greatest enigmas in modern cosmology, a mysterious force causing our universe to expand at an accelerating rate, as if some invisible hand is stretching the fabric of spacetime itself. But what if this force isn't acting alone? The cosmic mirror theory suggests a tantalizing possibility. Dark energy in our universe might have a counterpart in its mirrored twin, a shadow force balancing the cosmic scales. Picture two sides of a seesaw, with our universe's expansion matched by an equal and opposite reaction in the mirror world. This isn't just poetic symmetry. It could be the key to solving one of physics' most stubborn puzzles, the cosmological constant problem. The problem arises when we compare theoretical predictions about dark energy's strength with what we actually observe. Quantum mechanics suggests the vacuum of space should be teeming with energy, enough to rip the universe apart almost instantly. Yet in reality, dark energy's effects are far weaker, off by a factor of 10 to the power of 120. That's like predicting an ocean but finding only a single drop. This staggering discrepancy has left physicists scratching their heads for decades. But if a mirror universe exists, its dark energy might cancel out part of ours, like two opposing waves smoothing each other out. The tiny residue we detect could simply be the imbalance between these two cosmic forces. Here's where things get even wilder. If the mirror universe's time flows backward, its dark energy might behave inversely to ours. While our cosmos accelerates outward, the mirrored one could contract, its dark energy pulling everything inward like a cosmic inhale. This wouldn't just balance the equations, it would create a breathtaking dance of expansion and contraction across the twin realities. Some theories even propose that the mirror universe's contraction could explain why our own expansion is speeding up, as if the two are locked in a gravitational tug of war through higher dimensions. The implications ripple through our understanding of the universe's fate. Without a mirror counterpart, dark energy's dominance suggests a lonely future where galaxies drift apart into eternal cold. But with a balancing force in play, the cosmic story could have a very different ending or beginning, depending on which universe you're in. Perhaps the accelerating expansion we see isn't a one-way ticket to emptiness but part of a grander cycle, with the mirror universe's contraction eventually drawing everything back together in a cosmic reset. Of course, proving this idea isn't simple. Dark energy is notoriously elusive, and its mirror twin would be even harder to detect, but subtle clues might lie in the large-scale structure of the cosmos. If the mirror universe's gravity subtly influences ours, it could leave faint fingerprints in the distribution of galaxies or the cosmic microwave background. Future telescopes mapping the universe in unprecedented detail might spot these anomalies, revealing the hidden hand of a mirrored reality. The beauty of this idea lies in its elegance. The cosmological constant problem has long been seen as a glaring flaw in our theories, an ugly mismatch begging for resolution. The mirror universe offers a way to restore balance, not by discarding our current understanding but by expanding it literally. It suggests that the answers we seek might not lie solely in our universe but in its reflection, a realm where every force, every particle, and every law of physics has its perfect counterpart. The next time you look up at the night sky, consider this. The darkness between the stars might not be empty at all, but a window into a world where everything we know is inverted, and where the secrets of dark energy are waiting to be uncovered. Black holes have long captivated our imagination, cosmic vacuum cleaners swallowing everything that crosses their event horizons, even light itself. But in a mirror universe where time flows backward, these gravitational monsters might have bizarre twins, white holes. Imagine a black hole in reverse, a celestial fountain endlessly spewing out matter and energy instead of devouring it. While black holes trap everything inside their crushing grip, white holes would violently repel anything trying to enter, as if space itself were pushing back. The math behind these exotic objects isn't just speculative. It emerges naturally from Einstein's equations of general relativity when you flip the sign of time. The idea becomes even more intriguing when we consider how white holes might connect to the cosmic mirror theory. If our universe has a twin where time runs backward, could black holes here be linked to white holes there? Some physicists speculate that matter falling into a black hole in our cosmos might emerge from a white hole in the mirrored reality, creating a one-way bridge between the two. It's as if the two universes share a hidden plumbing system, with black holes acting as drains in our world and white holes as faucets in the other. This isn't just wild speculation, there's mathematical support for the idea. Solutions to Einstein's equations describe wormholes, theoretical tunnels through spacetime that could connect distant regions or even different universes. While traditional wormholes are notoriously unstable, requiring exotic matter to stay open, the mirror universe framework offers a potential workaround. If the two realities are quantum entangled at a fundamental level, the connection might be self-sustaining, held together by the symmetry between them. But why haven't we observed white holes if they exist? One possibility is that they're incredibly short-lived, exploding into existence and vanishing almost instantly in our forward-flowing time. From the perspective of the mirror universe, however, these events might unfold more gradually, like a slow-motion replay of our cosmic fireworks. Alternatively, white holes could be hidden behind event horizons of their own, visible only to observers in the backward-flowing reality. The implications are staggering. If black holes and white holes truly form bridges between universes, they might not just transport matter, they could carry information, energy, or even the arrow of time itself. Some theories suggest that the singularity at a black hole's heart might not be a dead end but a gateway, a point where the fabric of reality folds over to connect with its mirror image. This would mean that the fate of matter falling into a black hole isn't destruction but transformation, a journey into a world where every law of physics is flipped. Of course, major challenges remain. White holes violate the second law of thermodynamics in our universe, seemingly creating order from nothing. But in a mirrored cosmos where entropy decreases, this might be the norm. The real test will come as astronomers gather more data about black hole mergers and the mysterious flashes of energy sometimes detected in deep space. Could some of these events be echoes from the other side, faint signals of a white hole's outburst resonating through the cosmic mirror? The beauty of this idea lies in its symmetry. Just as the cosmic mirror theory suggests a balanced duality for matter and antimatter, time and space, it might also provide the missing piece to the black hole puzzle. These cosmic extremes, the ultimate consumers and the ultimate creators, could be two sides of the same coin, forever linked across the divide of opposing realities. Whether white holes exist or not, their theoretical possibility pushes us to rethink the boundaries of the possible, reminding us that the universe might be far stranger and far more interconnected than we ever imagined. Quantum entanglement has been called spooky action at a distance by Einstein himself, and for good reason. When two particles become entangled, they share a mysterious connection that defies our everyday intuition. Change one, and its partner instantly reflects that change, no matter how far apart they are. This phenomenon has been demonstrated in experiments over and over, with particles separated by hundreds of miles still acting as if they're in direct communication. But what if this quantum weirdness isn't just happening within our universe? The cosmic mirror theory suggests an even more mind-bending possibility. Entangled particles might not just be linked across space, but across realities, forming bridges between our universe and its backward-flowing twin. Think of entanglement like a pair of dice that always land on matching numbers, no matter how far apart you roll them. Now imagine one die exists in our universe while the other is in the mirror cosmos, where time flows in reverse. If you roll the die here and get a 3, its entangled counterpart in the mirror universe would simultaneously show a 3 as well, but from their perspective, the effect might appear to happen before the cause. This isn't just a theoretical curiosity. It could fundamentally alter our understanding of non-locality, the idea that objects can influence each other without any physical connection. If entanglement spans mirrored realities, it might reveal a hidden layer of the cosmos where time's arrow doesn't constrain quantum connections. The implications for quantum communication are staggering. In our universe, quantum entanglement is already being harnessed for ultra-secure encryption and potentially faster than light information transfer, though not in the way sci-fi might suggest. But if entangled pairs can link two universes with opposite time directions, could we someday send signals across the cosmic mirror? The challenge is that any attempt to manipulate an entangled particle here would be as unpredictable from the mirror universe's perspective as their actions would be to us. It's like two people trying to coordinate a dance while moving in opposite directions through time. What looks like a step forward to one is a step backward to the other. This raises profound questions about causality. In our world, we assume causes always precede effects, but in a mirrored reality, that sequence could be inverted. If entangled particles truly connect these two realms, they might form exceptions to the usual rules, creating pockets of symmetry where time's flow becomes ambiguous. Some physicists speculate that these quantum bridges could help resolve long-standing paradoxes, like why the universe appears fine-tuned for life. Perhaps the apparent precision of physical constants isn't accidental, but emerges from a balancing act between our universe and its mirror counterpart. Experiments might already be hinting at this deeper connection. Certain anomalies in quantum measurements, tiny deviations from what theory predicts, could be whispers from the other side, subtle nudges from particles entangled with their mirror twins. Future research could look for patterns in these anomalies, searching for signatures of a hidden cosmic symmetry. If found, it would be like discovering a message in a bottle, washed ashore from a parallel world where everything runs in reverse. The beauty of this idea is how it transforms entanglement from a mere curiosity into a potential window on reality's deepest structure. What we've been calling spooky action might actually be the universe's way of maintaining balance, a cosmic conversation between two realms that are forever linked yet forever separate. Whether this conversation can ever be decoded remains one of quantum physics' most tantalizing mysteries, one that might require us to rethink not just how particles interact, but how time itself weaves the fabric of existence. Every morning when you pour cream into your coffee and watch it swirl and mix, you're witnessing something profound, the arrow of time in action. This irreversible blending is a tiny example of entropy increasing, a process that defines why we remember the past but not the future. The second law of thermodynamics tells us that in closed systems, disorder always grows over time, creating an unmistakable directionality to events. Eggs scramble but never spontaneously unscramble, ice cubes melt but don't reform in warm drinks, and memories accumulate in one direction only toward what we call the future. Yet this familiar flow might not be as universal as it seems. The cosmic mirror theory flips this notion on its head. proposing that our experience of time's arrow could be just one half of a grander symmetry. In the mirror universe, entropy might decrease over time, creating a reality where shattered glass shards leap back into whole panes, where smoke funnels neatly into cigarettes, and where heat flows from colder objects to hotter ones. From our perspective, such events would look bizarrely backward, but to inhabitants of the mirrored cosmos, they'd feel as natural as our own forward-flowing time. This duality raises a radical question. Is the arrow of time an absolute feature of reality, or just a local condition of our cosmic neighborhood? The fundamental laws of physics, from Newton's mechanics to quantum field theory, don't actually require time to flow in one direction. The equations work just as well whether time runs forward or backward. Only when we zoom out to macroscopic scales does entropy's relentless rise create the illusion of an irreversible timeline. The mirror universe hypothesis suggests that the Big Bang might have set initial conditions for both realities, giving our cosmos a low entropy starting point, making the past appear orderly and the future chaotic, while giving the mirror universe the opposite, a high entropy starting point that trends toward order as time progresses. Quantum decoherence adds another layer to this puzzle. When particles interact with their environment, their quantum states become entangled and spread out, effectively locking in the arrow of time we experience. But in a mirror universe, this process could run in reverse, with quantum systems becoming more coherent over time instead of less. Imagine a drop of ink dispersing in water. That's decoherence in our world. Now picture the ink particles spontaneously regrouping into a single droplet. That might be the mirror universe's quantum reality. The strangest implication is how causality would operate across these two realms. In our universe, causes always precede effects, but in the mirror cosmos, effects might precede causes from our perspective. A mirror universe inhabitant might remember their future and anticipate their past, with every event unfolding in perfect reverse. This doesn't mean their reality is any less valid, just that their arrow of time points in the opposite direction, like two rivers flowing away from the same mountain peak. What's truly humbling is realizing how deeply our perception shapes our understanding of time. We assume time's flow is objective because our brains are wired to experience it that way. But the mirror universe hypothesis challenges this assumption, suggesting that time's direction might be more like a perspective, a viewpoint that flips depending on which side of the cosmic mirror you're standing on. The next time you watch cream swirl in your coffee, consider this. Somewhere in a mirrored reality, that same cup might be doing the exact opposite, unraveling its mixed chaos into perfect order, one backward moment at a time. The multiverse has long captured our imagination with visions of infinite realities, each a slight variation on our own, where every possible outcome plays out somewhere. Maybe in one universe, dinosaurs never went extinct, while in another, you chose a different career path. These parallel worlds, born from theories like eternal inflation or the many worlds interpretation of quantum mechanics, are like distant cousins, separate, independent, and unaware of each other. But the cosmic mirror theory paints a very different picture. Instead of countless disconnected realities, it proposes a single, intimate counterpart, a universe not just parallel to ours but bound to it by the fundamental symmetries woven into the fabric of existence. Think of it like a dance. Parallel universes are strangers moving to their own music in separate rooms, while mirror universes are partners waltzing in perfect synchrony, one stepping forward as the other steps back, their movements forever intertwined. This connection isn't just poetic, it's mathematical. Where parallel universes might differ randomly, perhaps with altered physical constants or rewritten histories, a mirror universe is our precise opposite, a reflection obeying strict symmetry rules like CPT invariance. Every proton here has an antiproton there. Every clockwise spin becomes counterclockwise, and every moment we experience as the future is, for them, the past. This symmetry creates fascinating possibilities that parallel universes can't match. Take quantum entanglement, for example. In the multiverse model, entangled particles might correlate across branches of reality, but in the mirror universe framework, they could bridge two entire cosmoses. A particle here and its entangled twin, they wouldn't just share states, they'd embody the symmetry between forward and backward time, offering a tangible link between the two worlds. Then there's the question of origins. Parallel universes often arise from chaotic processes like quantum fluctuations or bubble nucleation in an eternally inflating cosmos. But a mirror universe emerges from order, from the elegant symmetries baked into physics itself. It's the difference between a sprawling, untamed forest and a meticulously crafted kaleidoscope, where every fragment on one side has a deliberate counterpart on the other. Perhaps most intriguing is how these models handle the arrow of time. In most parallel universe theories, time flows the same way everywhere forward, with entropy increasing. But the mirror universe flips this script, suggesting that time's direction might not be absolute but relative, a local feature rather than a cosmic constant. This isn't just another reality, it's a reality that completes ours, balancing the cosmic equation in ways parallel worlds never could. The distinction matters because it changes how we search for evidence. Hunting for parallel universes might involve scouring the cosmic microwave background for collision scars from other bubbles or probing quantum decoherence for branching timelines. But detecting a mirror universe would mean looking for subtler signatures, anomalies in particle behavior that hint at CPT violations, asymmetries in the distribution of matter and antimatter, or even echoes of reverse time events in high-energy physics experiments. Ultimately, the cosmic mirror theory doesn't just add another room to the multiverse's endless mansion, it holds up a looking glass to our own reality, revealing that the universe we know might be half of a grander, more symmetrical whole. Whether through the mathematics of quantum fields or the mysteries of dark matter, the clues are mounting that our cosmos might not be alone, not in the chaotic crowd of parallel worlds, but in the intimate embrace of its own perfect reflection. Detecting a mirror universe might sound like science fiction, but physicists have devised several ingenious ways to search for its fingerprints in our own reality. One promising avenue lies in particle colliders like the Large Hadron Collider, where scientists smash protons together at nearly the speed of light. If a mirror universe exists, some particles produced in these violent collisions might occasionally vanish, as if slipping through an invisible barrier into the mirrored realm. Even stranger, we might spot particles behaving in ways that defy our current understanding of physics, subtle anomalies that could be evidence of interactions with their mirror counterparts. These wouldn't be dramatic disappearances, but tiny statistical quirks in collision data, like dice rolls that consistently come up slightly off what probability predicts. Gravitational waves, ripples in spacetime from cosmic cataclysms like black hole mergers, could also carry whispers from the mirror universe. Just as sound waves bounce off walls to create echoes, gravitational waves might interact with the boundary between our universe and its twin, producing faint secondary signals. Advanced detectors like LIGO and future observatories in space could potentially pick up these ghostly reverberations, revealing distortions that suggest the presence of a hidden cosmic mirror. Some theories even propose that certain gravitational wave patterns might appear reversed or time-shifted, as if we're hearing the cosmic drumbeat from the other side of reality. Then there's the mystery of neutrinos, those ghostly particles that barely interact with matter, certain types called sterile neutrinos might actually be messengers from the mirror universe, flitting between realities like cosmic shadows. Experiments like the upcoming Deep Underground Neutrino experiment are specifically designed to hunt for these elusive particles. If they detect neutrinos oscillating in unexpected ways or appearing and disappearing without explanation, it could hint at a doorway to the mirrored cosmos. Perhaps the most mind-bending possibility involves quantum entanglement. If particles in our universe can become entangled with their mirror counterparts, measuring one might instantaneously affect the other, even across the divide of time reversal. While we couldn't use this to send messages, the randomness of quantum mechanics prevents that. Carefully designed experiments might reveal correlations that defy any explanation except a connection to a backward-flowing reality. The challenge, of course, is distinguishing true mirror universe signals from ordinary statistical noise or unknown physics within our own cosmos. That's where next-generation telescopes and particle detectors come in. As our instruments grow more sensitive, the subtle anomalies that might reveal the mirror universe could emerge from the background like a faint image developing in a photographer's darkroom. It might take years or even decades of painstaking observation, but the payoff would be revolutionary. Not just discovering another universe, but finding one that's intimately tied to our own through the deepest symmetries of reality. Until then, every unexplained blip in the data, every slight deviation from theory, carries the thrilling possibility that we're glimpsing the edge of the cosmic looking glass. Neutrinos are the cosmic ghosts of the particle world, so ethereal that trillions pass through your body every second without a single interaction. These nearly massless particles, born in the hearts of stars and violent cosmic events, barely notice the existence of matter, slipping through planets like sunlight through glass. But what if their elusive nature isn't just a quirk of physics? The cosmic mirror theory proposes that neutrinos, particularly a hypothetical variety called sterile neutrinos, might be the universe's secret messengers whispering clues about a mirrored reality where time flows backward and physical laws invert. Sterile neutrinos are particularly intriguing because they don't even interact via the weak nuclear force, the usual handshake mechanism for their more social neutrino cousins. If they exist, they'd be even more ghostly than ordinary neutrinos, potentially passing effortlessly between our universe and its mirror twin. Some theories suggest that sterile neutrinos could oscillate, morphing between regular and mirror-flavored versions as they travel. Imagine a cosmic game of peekaboo where particles flicker in and out of our reality, leaving behind telltale gaps in experimental data. These missing energy signatures, detected in experiments like the Mini-BUANI project at Fermilab, might not be measurement errors but footprints of particles momentarily stepping into the mirror world. The implications stretch far beyond particle physics. If sterile neutrinos bridge the two universes, they might explain one of cosmology's lingering mysteries, dark matter. The mirror universe's particles, invisible to our detectors except through gravity, could account for the missing mass bending galaxies and shaping the cosmos. In this scenario, dark matter wouldn't just be an exotic substance, it might literally be the shadow of another reality, its gravitational pull the only sign of a vast, hidden cosmic twin. Experiments are already hunting for these phantom particles, deep underground where thick layers of rock shield detectors from cosmic noise. Scientists watch for the rare flashes that signal a neutrino interaction. Projects like the upcoming Deep Underground Neutrino experiment are fine-tuned to catch anomalies, unexpected oscillation patterns, or energy discrepancies that could hint at sterile neutrinos slipping between dimensions. Even more tantalizing are proposals to study supernova neutrinos. When a star explodes, it floods the cosmos with these particles, offering a natural high-energy lab. If a supernova's neutrino burst shows inexplicable delays or missing flavors, it might mean some particles took a detour through the mirror universe before arriving here. The beauty of this idea lies in its symmetry. Just as neutrinos barely interact with matter, their mirror counterparts would barely interact with ours except through gravity and perhaps these subtle quantum oscillations. It's as if the universe designed the perfect intermediaries for two realms never meant to fully touch. The next time you hear about a neutrino experiment coming up empty or detecting an anomaly, consider this. The absence of evidence might actually be evidence of a hidden cosmos, perfectly balanced against our own, communicating through the faintest, most ghostly particles in existence. The story of cosmic inflation reads like the ultimate growth spurt a fraction of a second after the Big Bang. Our universe expanded exponentially, stretching from smaller than an atom to something approaching cosmic scale. This explosive growth smoothed out the wrinkles of space-time, leaving behind the remarkably uniform cosmic microwave background we observe today. But what if this inflationary period wasn't a solo act? The cosmic mirror theory suggests an extraordinary possibility. While our universe ballooned outward, its twin might have undergone the exact opposite, a cosmic contraction, as if the two realities were breathing in and out in perfect counterbalance. Picture two sides of an accordion. As one side expands, the other compresses. If inflation in our universe was matched by deflation in the mirror world, it could explain why the large-scale structure of the cosmos appears so finely tuned. The slight density variations we see in galaxy clusters, the seeds that eventually grew into stars and planets, might not be random quantum fluctuations but echoes of this symmetry, imprinted when the two universes were still entangled in their infancy. Some models even propose that the mirror universe's contraction could have acted like a cosmic stabilizer, preventing runaway inflation from tearing our reality apart before matter could form. The implications ripple through our understanding of the early universe. Inflation famously solves several cosmological puzzles, like why the universe appears so flat and uniform in every direction. But it also raises questions: what triggered this rapid expansion, and why did it stop so abruptly? A mirror universe offers an elegant answer. The energy driving inflation in our world might have been counterbalanced by negative energy in the mirrored realm, creating a natural braking mechanism. Think of it like a cosmic seesaw, with the two universes trading energy back and forth until equilibrium was reached. This duality might also shed light on one of inflation's lingering mysteries, the so-called multiverse problem. If inflation never truly stops in some regions, it could spawn an endless cascade of bubble universes. But if a mirror universe exists, its deflationary phase might provide a natural cutoff, limiting runaway expansion and keeping the multiverse in check. Instead of infinite disconnected bubbles, we'd have a paired structure, each inflating universe tethered to a contracting twin, like opposite ends of a cosmic teeter-totter. The most tantalizing clue might lie in the cosmic microwave background itself. The faint temperature variations we've mapped across the sky could contain subtle asymmetries, patterns that look like fingerprints of a mirror universe's gravitational influence. Future telescopes, like the European Space Agency's Euclid mission, might detect these anomalies, revealing whether the universe's large-scale structure bears the marks of a hidden counterpart. What's truly staggering is the idea that the mirror universe's deflation wouldn't just be a historical footnote. It might still be happening. While our cosmos continues expanding, its twin could be collapsing toward an eventual big crunch, a reversal of the Big Bang where all matter and energy converge back into a singularity. If true, this means the mirror universe's fate isn't just a reflection of our past but a glimpse of a possible future. one where time, space, and physical laws fold back in on themselves, completing the grand symmetry that began at the dawn of existence. The Fermi paradox has haunted astronomers for decades. If the universe is so vast and ancient, why does it seem so empty of intelligent life? The silence feels eerie, like walking through a city where every building stands ready but not a single soul stirs inside. Now, imagine adding a mirror universe into the mix, a reality where time flows backward and physical laws invert. Suddenly, the paradox takes on new layers of mystery. Could intelligent life flourish in such a mirrored cosmos? And if so, why haven't we glimpsed even a hint of its existence? Life in a backward-flowing universe would face challenges we can scarcely imagine. Consider evolution, a process that, in our world, relies on increasing complexity over time. In the mirror universe, evolution might work in reverse, with life forms starting highly complex and simplifying over eons. Picture a towering alien civilization gradually devolving into single-celled organisms as time progresses from their perspective. Communication would be equally baffling. Any signal they send would arrive in our universe before it was transmitted from their viewpoint, like receiving a reply to a letter you haven't written yet. The arrow of time also shapes how intelligence emerges. In our universe, consciousness depends on memory, a record of past experiences guiding future actions. But in the mirror reality, beings might remember the future and anticipate the past, their minds wired to process causality in reverse. Would they even recognize us as intelligent, or would our forward-thinking brains seem as alien to them as their backward-flowing cognition seems to us? Then there's the technological hurdle. Civilizations in the mirror universe might harness energy in ways that defy our understanding. While we extract energy from splitting atoms or burning fuel, they could exploit processes where energy spontaneously concentrates, like heat flowing from cold to hot. Their technology might appear to us as perpetual motion machines, breaking the second law of thermodynamics because, for them, entropy decreases naturally. But the real twist lies in the Fermi paradox itself. If mirror universe life exists, why wouldn't they have reached out? The answer might lie in the nature of time's flow. From our perspective, any attempt they make to contact us would appear to happen before they even conceived of it, like an echo preceding the shout. Signals might be lost in the noise of cosmic radiation, misinterpreted as random fluctuations rather than deliberate messages. Alternatively, the mirror universe's inhabitants could be just as isolated as we are, staring into the void and wondering why they're alone. Their telescopes might peer into our universe, seeing galaxies that, from their perspective, are aging backward, stars unexploding, planets reforming from dust, a spectacle as bewildering to them as their reality is to us. The chilling possibility remains that life in a mirrored cosmos is impossible, that the inverted flow of time prevents the delicate chemical processes needed for biology. Or perhaps civilizations arise only to vanish as their arrow of time carries them toward simplicity, like sandcastles dissolving with each receding wave. What's certain is that the mirror universe adds a dazzling new dimension to the Fermi paradox. It's no longer just about where extraterrestrials are, it's about when they exist and in which direction they're now points. The silence of the cosmos might not mean we're alone after all, but that we're listening for voices moving through time the wrong way. Time travel has long been the stuff of science fiction, but the cosmic mirror theory forces us to reconsider what it might mean in a universe where time runs backward by default. If the mirror cosmos exists with its inverted arrow of time, does that automatically open the door to time travel in our own reality? The answer lies somewhere between groundbreaking physics and the limits of what we can truly know. Let's start with the basics. In our universe, time travel to the past is fraught with paradoxes. The grandfather paradox is the most famous. What happens if you go back and prevent your own birth? The very act creates a logical inconsistency that seems impossible to resolve. But in a mirror universe where cause and effect are reversed, these paradoxes might not be paradoxes at all. Imagine an event in the mirror cosmos where an effect precedes its cause from our perspective, like a fire starting before the match is struck. To inhabitants of that reality, this would feel perfectly natural, just as our forward-flowing causality feels natural to us. The mirror universe doesn't so much solve time travel paradoxes as it reframes them, suggesting that what we consider impossible might simply be a limitation of our one-directional experience of time. This doesn't mean we could hop into a time machine and visit the past, but it does imply that the past, or at least a version of it, might still exist in some form, playing out in reverse on the other side of the cosmic mirror. The real question is whether any crossover between these two timelines is possible. Some theories propose that black holes in our universe might connect to white holes in the mirror cosmos, creating a one-way bridge where matter from our present falls in and emerges in their past. But this isn't time travel as we imagine it, no free will, no changing history. Instead, it's more like a cosmic conveyor belt with events unfolding in lockstep according to the symmetries of physics. Any attempt to exploit this connection would run into the same fundamental limits that prevent faster-than-light communication. Causality must be preserved, even across mirrored realities. What's fascinating is how this framework reinterprets classic time travel stories. In films like Back to the Future, altering the past creates branching timelines. But in the mirror universe model, there are no branches, just two realities moving in opposite directions, each influencing the other in ways that maintain balance. If you could somehow send a message backward into the mirror universe, it wouldn't rewrite history. It would simply be part of the unbroken chain of cause and effect from their perspective. The paradoxes we fear might just be artifacts of our limited view, like a two-dimensional creature trying to comprehend depth. The mirror universe doesn't promise us time machines, but it does challenge our assumptions about time's rigidity. If the arrow of time is a local phenomenon rather than an absolute rule, then the past and future might be more fluid than we ever imagined. The next time you watch a time travel movie, consider this. The most plausible version of the story might not involve hopping into a DeLorean, but peering into a universe where time's flow is inverted, a place where every moment we consider gone is still unfolding, just in reverse. The holographic principle turns our understanding of reality inside out, literally. Imagine the entire cosmos not as a three-dimensional expanse, but as a two-dimensional surface, like a cosmic DVD encoding every star, galaxy, and atom as information etched on its boundary. This isn't just a metaphor, it's a serious hypothesis born from black hole physics, where the amount of information a black hole can hold scales with its surface area, not its volume. Now layer this with the cosmic mirror theory, and things get even stranger. If our universe is a hologram, could its mirror twin be part of the same projection, a flipped image encoded alongside ours on the boundary of reality? Think of it like a vinyl record with two sides. The holographic boundary might encode both universes simultaneously, our forward-flowing reality on one track, and its time-reversed counterpart on the other. The vibrations of the cosmic needle, quantum fluctuations in the higher dimensional boundary, would then translate into the events we experience as time and space. This would mean the mirror universe isn't just a separate entity, but an inseparable part of a unified holographic structure, like the positive and negative spaces in an optical illusion. The math behind this is as elegant as it is mind-bending. In holographic models, phenomena like quantum entanglement, which already hints at deep connections between distant particles, might emerge from threads of information woven across the boundary surface. If the mirror universe shares this encoding, entanglement could take on a new dimension. Particles in our world might be linked to their inverted twins not just across space but across the holographic divide itself. It's as if the universe's source code has a built-in symmetry, with every line of ours mirrored by a corresponding line running backward. This perspective could solve one of holography's lingering puzzles: why our universe appears so finely tuned for complexity. If the hologram encodes two realities in balance, the apparent fine-tuning might simply be the shadow of that symmetry. Dark energy's inexplicably small value, for instance, could reflect a cancellation effect between our universe's expansion and the mirror universe's contraction, both encoded on the same boundary. But how would we ever test such an abstract idea? Surprisingly, there might be observable clues. If the mirror universe is holographically linked to ours, subtle correlations could appear in the cosmic microwave background, patterns too precise to be random, like faint interference fringes between two projected images. Future space telescopes designed to map the universe's large-scale structure with unprecedented detail might spot these anomalies, revealing the hidden seams in reality's fabric. The beauty of this synthesis is how it unites two radical ideas into something even grander. The holographic principle suggests we're living in a shadow play, while the cosmic mirror theory insists there's another actor sharing the stage. Together, they paint a picture of existence as a dynamic interplay between surface and depth, forward and backward, one and its reflection. Whether this vision holds up under scrutiny remains to be seen, but it undeniably reshapes how we see the cosmos, not as a solitary universe, but as one half of a holographic dialogue, whispering across the boundary of dimensions. String theory has always pushed the boundaries of what we consider possible, proposing that the fundamental building blocks of reality aren't particles but tiny vibrating strings. These strings thrum through not just the familiar 4 dimensions, 3 of space and 1 of time, but through 6 or 7 additional dimensions curled up so small we can't perceive them. Here's where things get truly fascinating. What if some of these hidden dimensions aren't just extra spatial directions but gateways to a mirrored reality? The cosmic mirror theory might find its most natural home in the intricate mathematics of string theory, where higher dimensions could host an entire universe running in reverse. Picture a Möbius strip, a surface with only one side that twists back on itself. String theory's extra dimensions might operate similarly, folding space in ways that create natural mirrors. In some formulations, vibrations moving clockwise through these dimensions could correspond to particles in our universe, while counterclockwise vibrations might represent their mirror counterparts. This isn't just mathematical whimsy. It's a potential solution to one of string theory's biggest challenges, the landscape problem, which suggests an almost infinite number of possible universes with different physical laws. A mirror universe pairing could restore balance, taming this chaotic multiplicity with elegant symmetry. The connection goes deeper when we consider D-brane's membranes in string theory, where strings can attach. Some physicists speculate that our universe might be a 3-dimensional brane floating in a higher dimensional bulk, with a parallel brane hosting the mirror universe just a tiny distance away in an extra dimension. The mind-bending implication: particles in our world could have shadows on the mirror brane, interacting only through gravity, which might explain why we've yet to detect these extra dimensions directly. It's as if we're living on one side of a vast cosmic sheet of paper, with another reality pressed invisibly close on the reverse side. String theory also offers a fresh perspective on time's arrow. In traditional physics, time's forward flow feels absolute, but string theory allows for more flexibility. Certain solutions describe time-reversed worlds coexisting with ours in the higher dimensional landscape, like reflections in a multi-dimensional hall of mirrors. These models don't just accommodate the cosmic mirror theory, they demand it, treating our universe and its twin as two sides of the same vibrational coin. The strings making up your body in this reality might have inverted counterparts vibrating in perfect opposition elsewhere, their combined motions cancelling out to maintain cosmic harmony. Yet challenges remain. String theory famously struggles with experimental verification, and the mirror universe hypothesis adds another layer of complexity. If extra dimensions are compactified at scales 1 billion times smaller than an atom, how could we ever detect their mirrored inhabitants? Some researchers propose looking for gravitational anomalies, subtle deviations from Einstein's predictions that might hint at gravity leaking between branes. Others suggest that high-energy particle collisions could momentarily excite these hidden dimensions, producing signatures like missing energy or unexpected particle decays. The true power of this synthesis lies in its unifying potential. String theory seeks to reconcile quantum mechanics with gravity, while the cosmic mirror theory aims to explain cosmic asymmetries. Together, they paint a picture where the universe's deepest imbalances, like the matter-antimatter disparity, are resolved not by adding new particles or forces, but by recognizing that we're seeing only half of a grander, multidimensional whole. The next time you hear about string theory's elusive extra dimensions, consider this. They might not just be mathematical abstractions, but the hidden architecture of a reality twice as vast and twice as strange as we ever imagined. Dark matter is the universe's most persistent ghost, an invisible presence that bends galaxies and sculpts the cosmos, yet slips through our detectors without a trace. We know it's there because of its gravitational grip on stars and galaxies, but what it's made of remains one of science's greatest unsolved puzzles. The cosmic mirror theory offers a radical explanation. What if dark matter isn't just an unknown particle in our universe, but ordinary matter from a mirrored reality, one where time flows backward and physical laws invert? Imagine a world identical to ours in substance but opposite in symmetry, its particles drifting through ours like shadows, felt only through their gentle gravitational tug. This idea isn't as far-fetched as it sounds. If the mirror universe exists, its matter would naturally interact with ours almost exclusively through gravity, the only fundamental force that doesn't depend on charge or time direction. Just as you can see your reflection in a window but can't reach through to touch it, mirror matter might permeate our world while remaining frustratingly out of reach. Every galaxy in our universe could be paired with a shadowy counterpart in the mirror cosmos, their combined gravity explaining why galaxies rotate faster than visible matter alone can account for. The extra mass we attribute to dark matter might simply be the weight of another reality pressing invisibly against our own. But how would this differ from traditional dark matter candidates like WIMP or actions? The key lies in the symmetry. Mirror matter wouldn't require inventing new particles or forces. It would leverage the ones we already know, just flipped. A mirror proton would have the same mass as ours but opposite charge parity. A mirror electron would spin the other way. These particles wouldn't respond to our electromagnetism or nuclear forces, making them undetectable by conventional means. Yet their gravitational influence would be identical, neatly explaining why dark matter's effects are so pervasive yet so elusive. Critics raise valid concerns, though. If mirror matter is so abundant, why don't we see more direct evidence of its gravitational distortions, like unique lensing patterns or anomalies in galaxy collisions? Some models suggest mirror matter might clump differently than ordinary matter, forming diffuse halos rather than dense structures. Others propose that the mirror universe's expansion history could leave subtle imprints on the cosmic web's architecture, threads of galaxies aligned in ways that hint at an unseen partner's pull. Future sky surveys like the Vera Rubin Observatory might spot these cosmic breadcrumbs, revealing whether the universe's large-scale structure bears the fingerprints of a hidden twin. The most tantalizing possibility is that dark matter isn't just a passive shadow but an active participant in cosmic evolution. If mirror stars and planets exist, their gravity could subtly shepherd the birth of galaxies in our world, like invisible hands shaping clay. Supernova in the mirror universe might send ripples through shared spacetime, nudging celestial bodies in ways we've yet to decipher. Even life's origins could be entangled. What if Earth's primordial soup was stirred by the gentle tide of a mirror moon's gravity? Of course, the mirror matter hypothesis isn't without competition. Alternative explanations from primordial black holes to modified gravity still vie for dominance. But what sets the mirror universe apart is its elegance. It doesn't just solve the dark matter puzzle. It weaves it into a grander symmetry, linking one of cosmology's biggest mysteries to the fundamental laws of physics. Whether this idea holds up under scrutiny will depend on the next generation of experiments, from ultra-sensitive dark matter detectors to precision maps of the cosmic microwave background. Until then, every unexplained gravitational flicker, every anomalous orbital dance, could be a whisper from the other side of reality, a reminder that the universe's secrets might not just be hidden in the darkness, but in the mirror. The Boltzmann brain paradox is one of the strangest thought experiments in physics, a cosmic glitch that makes you question whether your own thoughts can be trusted. Here's the unsettling premise. In an infinite, chaotic universe where particles randomly arrange themselves over incomprehensible timescales, there's a non-zero chance that a fully formed, self-aware brain could spontaneously assemble from the void, complete with false memories of a life that never happened. It sounds like bad sci-fi, but the math checks out. Given enough time, even the most improbable events become inevitable. So why don't we observe these disembodied minds floating through space? And more crucially, how do we know we're not Boltzmann brains, hallucinating reality in some fleeting moment of improbable order? This is where the mirror universe steps in with a potential escape hatch. If our cosmos has a twin where entropy decreases rather than increases, the Boltzmann paradox takes on a fascinating twist. In a backward-flowing reality, self-aware structures wouldn't emerge from chaos, they'd dissolve into it. Imagine a Boltzmann brain forming in our universe, only to immediately unravel in the mirror universe's opposing arrow of time. The two realities could act like cosmic bookends, preventing runaway fluctuations by canceling each other out. It's as if the universe installed a fail-safe. For every random, self-aware flicker in one world, there's an equal and opposite unraveling in the other. The implications ripple through our understanding of consciousness itself. If Boltzmann brains are statistically inevitable in an eternal, disordered cosmos, their absence suggests something fundamental is missing from the picture, a hidden mechanism that suppresses these aberrations. The mirror universe offers exactly that, a symmetry preserving the stability of reality. Just as matter can't exist without antimatter in balanced quantities, perhaps conscious observers can't emerge without their mirrored counterparts ensuring equilibrium. This wouldn't just resolve the paradox, it would imply that sentience, like everything else, is part of a grander duality. Critics argue that invoking a mirror universe to solve Boltzmann's riddle feels like stacking one extraordinary idea atop another. But consider this, the paradox arises because we assume time's arrow is absolute. If entropy's increase is just a local feature of our cosmic neighborhood, the math shifts dramatically. The probability of isolated consciousness flickering into existence plummets when you account for the mirror universe's opposing flow, like trying to light a match in a hurricane. Suddenly, the odds align with what we actually observe, a universe where minds like ours exist within sustained structures, not as fleeting accidents. The real magic of this solution lies in its elegance. It doesn't just patch a theoretical hole, it weaves consciousness into the fabric of cosmic symmetry. Every thought you have, every memory you cherish, might be mirrored somewhere in a reality where time flows backward, not as an illusion but as part of a balanced equation. The next time you doubt your own existence, take comfort in this. You're not a random fluctuation. You're half of a deeper, more profound pattern, one that stretches across the looking glass of space-time itself. The cosmic censorship hypothesis acts like nature's ultimate spoiler alert. It suggests the universe has built-in mechanisms to hide its most shocking twists from view. At its core, this principle states that singularities, those infinitely dense points at the center of black holes where physics breaks down, must always be concealed behind event horizons, never exposed for observers to see. It's as if reality has a privacy filter protecting us from its most extreme and unpredictable behaviors. Now, imagine applying this same logic to the mirror universe. If an entire reality exists where time flows backward and physical laws invert, why can't we detect it directly? The answer might lie in a grander form of cosmic censorship, where fundamental barriers prevent us from peering beyond the reflection's edge. Consider how black holes operate in our universe. The event horizon acts as a one-way curtain. Once crossed, nothing can escape, not even light. This creates a perfect information barrier, hiding the singularity's chaos from the outside world. A mirror universe might be protected by an analogous but even more profound boundary, not just a spatial divide but a dimensional one. Instead of an event horizon, the separation could involve higher dimensions or quantum decoherence effects that scramble any potential signals. Just as a black hole's interior remains forever inaccessible to outside observers, the mirror cosmos might be permanently veiled by the very symmetries that define it. This raises a fascinating possibility. What if the cosmic censorship we observe in black holes isn't just about hiding singularities, but about maintaining equilibrium between paired realities? The violent unpredictability of a naked singularity could be nature's way of preventing information leaks between universes. Any attempt to breach the barrier might trigger quantum effects that reinforce the separation, like a cosmic immune system rejecting foreign tissue. We see hints of this in the way black holes evaporate via Hawking radiation. Information seems lost forever, but some theories suggest it's merely translated into forms we can't yet decipher. Similarly, data from the mirror universe might be encoded in ways our instruments perceive as background noise or quantum fluctuations. The boundaries of observation grow even stranger when we consider quantum mechanics. In our world, measuring a particle's state collapses its wave function, forcing it to choose a definite position or momentum. But in a mirror universe where time runs backward, this process might appear. Inverted measurements could seemingly uncollapse wave functions, restoring quantum uncertainty. If the two realities are entangled at a fundamental level, our very attempts to observe the mirror world might trigger self-censoring mechanisms that preserve the symmetry. It's like trying to read a book where the words rearrange themselves the moment you focus on them, keeping the story just out of reach. Yet clues might lurk in the shadows of our detectors. Gravitational wave astronomy offers one potential window. subtle anomalies in the ripples from black hole mergers could hint at interactions with mirror matter. Particle physics experiments might spot statistical deviations suggesting momentary breaches in the cosmic firewall. Even the cosmic microwave background could hold patterns indicating gravitational lensing from invisible mirror galaxies. These wouldn't be direct observations any more than we can see a black hole's singularity, but their indirect effects might reveal the censorship's edges. The deeper question is whether this censorship is a bug or a feature. Is the mirror universe hidden because the laws of physics make detection impossible, or because some higher principle demands separation? Perhaps the universe protects itself from paradoxes the same way black holes shield us from singularities by erecting boundaries that preserve causality's integrity. After all, if we could freely interact with a reality where time flows backward, the potential for universe-breaking paradoxes would be endless. The cosmic censorship might not just be hiding something from us, it could be protecting both realities from each other. Ultimately, this pushes us to reconsider what observation even means in a multiverse context. Just as quantum particles exist in superpositions until measured, the mirror universe might hover in a state of potentiality real but unobservable, like the far side of a black hole's event horizon. The cosmos could be far richer than we perceive, not because it lacks evidence, but because the most fundamental laws prevent that evidence from ever reaching us intact. The next time you gaze at the night sky, remember you might be looking at only half the story, with the rest carefully redacted by reality itself. The multiverse isn't just one idea, it's a sprawling cosmic zoo filled with wildly different visions of reality. On one end, there's the inflationary multiverse, where countless bubble universes inflate endlessly, each with its own unique physics. On another, the many worlds interpretation of quantum mechanics suggests every decision spawns branching timelines, creating a fractal tree of alternate histories. And then there's the holographic multiverse, where lower dimensional boundaries encode higher dimensional realities like cosmic DVDs. So where does the mirror universe, a single, perfectly inverted twin, fit into this menagerie of possibilities? Unlike parallel worlds that multiply endlessly, the mirror universe is a minimalist's multiverse, one profound symmetry, one elegant counterbalance, a cosmic yin to our yang. What sets the mirror universe apart is its intimate connection to our own. While bubble universes float independently in an eternally inflating void, and branching timelines diverge unpredictably, the mirror cosmos is bound to ours by the unbreakable threads of fundamental physics. CPT symmetry isn't just a suggestion here, it's the law demanding that for every particle in our world, there's an antiparticle in the mirror. For every forward-flowing cause and effect here, a backward-flowing counterpart there. This isn't a random alternate reality, but a necessary shadow, a reflection required to keep the cosmic books balanced. Think of it like a dance partner rather than a stranger passing in the multiverse's halls, always in step, always opposite. The mirror universe also offers something most multiverse theories can't: testability. While bubble universes are forever beyond our observational horizon, and branching timelines remain locked in quantum superposition, the mirror cosmos might leave faint fingerprints in our reality. Anomalies in particle collisions, unexpected neutrino behaviors, or gravitational wave echoes could hint at its presence. This grounding in observable physics makes the mirror universe less a speculative fantasy and more a dramatic extension of symmetries we already know exist. It's the difference between imagining an infinite stack of unrelated worlds and discovering that your own reflection has been alive all along. Yet the mirror universe doesn't replace other multiverse theories, it complements them. Imagine a vast cosmic tree where branching timelines sprout from every decision, each branch hosting its own mirror twin. Or consider bubble universes where some bubbles contain single realities, while others harbor mirrored pairs. The holographic principle could encode not just our universe but its reflection on the boundary's flip side. This layered view transforms the multiverse from a chaotic jumble into a structured tapestry, with the mirror universe as its most intricate thread, a pattern repeating at every scale, from quantum entanglement to galactic superclusters. The real magic lies in how the mirror universe reframes the multiverse's greatest mysteries, the fine-tuning problem why our physical constants seem perfectly calibrated for life might not require divine intervention or infinite random trials. Instead, the delicate balance could emerge from the push and pull between our universe and its twin, like two sides of an equation canceling out to leave just the right residue for stars, planets, and consciousness. Even the arrow of time, often taken as an absolute in multiverse theories, becomes fluid, a local phenomenon rather than a universal rule. So is the mirror universe the multiverse's odd cousin or its secret backbone? Perhaps both. In a landscape teeming with wild possibilities, it stands apart not by being the strangest idea, but by being the most inevitable. The deeper we dig into physics symmetries, the harder it becomes to imagine our universe without its reflection. Whether it's the only alternate reality or one of countless, the mirror cosmos forces us to confront a humbling truth. Reality might not just be bigger than we imagined, but more beautifully balanced than we ever dreamed. Free will has always stood at the crossroads of science and philosophy, a fragile idea caught between the unbreakable laws of physics and our unshakable sense of personal agency. But toss a mirror universe into the mix, where every choice we make here might have an inverted counterpart there, and the debate takes on vertigo-inducing new dimensions. If time's arrow isn't absolute but merely a local quirk of our cosmic neighborhood, does that mean our decisions are just echoes of some grand, predetermined symmetry? The answer depends on which side of the looking glass you're standing. Consider a simple act: you choose to lift your hand. In our forward-flowing universe, this feels like a conscious decision. Neurons fire, muscles contract, and voila, your hand rises. But in the mirror cosmos, the same event unfolds in reverse. From their perspective, your hand lowers seemingly of its own accord, with the decision to lift it occurring afterward. This reversal doesn't negate free will, it redefines it. Instead of cause preceding effect, the mirror universe operates on effect anticipating cause, like a film played backward where the explosion happens before the fuse is lit. To its inhabitants, their sense of agency would feel just as real as ours, even if their choices appear predetermined from our vantage point. This duality forces us to confront the nature of determinism. If every action here has an equal and opposite reaction in the mirror universe, does that lock both realities into an unbreakable script? Not necessarily. Quantum mechanics introduces an element of fundamental unpredictability. Particles don't behave like clockwork but follow probabilities. In a mirrored cosmos, this uncertainty could manifest as freedom disguised as inevitability. Your decision in the mirror world might look predetermined to us, but from their perspective, it's as spontaneous as any choice feels in our own lives. The real twist comes when we consider entangled decisions across the cosmic divide. Imagine two versions of you, one here, one there, making what each perceives as independent choices, only for those choices to perfectly align through quantum symmetry. It's less about fate and more about harmony, like two dancers improvising yet always moving in sync. This doesn't diminish free will. It elevates it to a cosmic scale, where agency becomes a collaborative act between twin realities. Philosophers have long wrestled with compatibilism, the idea that free will and determinism can coexist. the mirror universe offers a radical new framework for this balance. Rather than a single timeline where every event is set in stone, we might have two interwoven narratives, each respecting the other's flow of time while maintaining their own internal logic. Your choices matter here because they're part of a larger dance, not in spite of it. Of course, skeptics argue that true free will requires complete independence from external constraints, mirror universe or not. But even in our everyday lives, freedom is never absolute. We make choices within the bounds of physics, biology, and circumstance. The mirror cosmos simply adds another layer to this complex tapestry, reminding us that agency isn't an illusion just because it's part of a bigger picture. What's truly humbling is how this reframes our place in the cosmos. We're not just actors on a stage, but participants in a cosmic duet, our forward-moving decisions harmonizing with a reality where time flows the other way. The next time you pause at a crossroads, weighing one path against another, consider this. Somewhere in a mirrored reality, another version of that moment is unfolding in reverse, not as a paradox, but as proof that free will might be far richer and far stranger than we ever imagined. Attempting to communicate with a mirror universe isn't just a scientific challenge, it's an ethical minefield. Imagine sending a message into the cosmic void, only to realize that every word you transmit arrives in the mirrored reality before you've even conceived of it. From their perspective, your first contact might appear as a bizarre echo of a conversation they initiated eons ago. This temporal inversion creates dilemmas we've never faced. Would reaching out violate some unspoken cosmic etiquette, or worse, trigger unintended chain reactions across realities? The risks aren't hypothetical. If the mirror universe's physics truly invert ours, a simple exchange of information could destabilize delicate quantum symmetries that keep both realities intact. Then there's the question of intent. Human history is littered with disastrous first contacts between civilizations, cultures clashing, diseases spreading, ecosystems collapsing. But that damage unfolded across linear time, allowing for course correction. A mirror civilization operating with inverted causality might interpret our overtures as hostile acts before we've even sent them. Picture a scenario where their defensive measures precede our message, like a missile striking before the declaration of war. The very act of saying hello could be misinterpreted as the closing statement of a conflict we didn't know had begun. Yet the potential rewards are equally staggering. A successful dialogue could unlock technologies harnessing entropy reversal or zero-point energy. Medical breakthroughs might emerge from studying mirror biology, where aging runs backward and diseases spontaneously heal. Even philosophical paradigms could shift. Imagine exchanging ideas with a culture that perceives time as a tapestry woven from future to past. They're solutions to problems we haven't encountered, yet might already exist in their historical records, offering us a roadmap to survival we couldn't have conceived independently. The stakes grow higher when considering entanglement. If particles in our universe are linked to their mirror counterparts, conscious communication could forge unpredictable bridges. A single synchronized experiment might create feedback loops cascading through both realities, like shouting into a canyon where the echoes grow louder instead of fading. Some models suggest that sustained interaction could temporarily synchronize arrows of time at the boundary, creating zones where entropy flows sideways, neither forward nor backward, but in some hybrid state defying all known physics. Perhaps the greatest ethical hurdle is consent. On Earth, we debate the ethics of broadcasting our presence to hypothetical aliens via projects like METI. But a mirror universe isn't just distant, it's fundamentally other. Its inhabitants might perceive communication attempts as physical violations, like neurons firing backward in their brains. Their concept of privacy could involve temporal boundaries we can't comprehend, making every transmission an inadvertent trespass. Until we understand whether consciousness in a reversed time universe even values connection as we do, diplomacy might be less like shaking hands and more like trying to hug a shadow. The irony is crushing. After centuries of searching the stars for companionship, we might discover our closest neighbors are separated not by space, but by the direction of time itself, close enough to touch, yet forever out of phase. The choice to reach across that divide isn't just scientific, it's a test of whether humanity can resist the temptation to poke realities we don't understand. Sometimes the most profound respect we can offer isn't a greeting, but silence, a willingness to let the mirror stay unbroken, even when we yearn to see what's staring back. The mirror universe isn't just a playground for theoretical physicists. It could be the key to unlocking technologies that sound like pure science fiction today. Imagine a power source that taps into the inverted entropy of a mirrored reality, where energy flows from cold to hot. In our world, heat death looms as entropy increases, but a device bridging both universes might harness the mirror cosmos's natural tendency toward order, creating a perpetual energy gradient. Think of it like a cosmic battery, with one terminal plugged into our universe's chaos and the other into the mirror world's spontaneous organization. The result, a reactor requiring no fuel, just the symmetry between realities. Quantum computing could leap forward by exploiting entanglement with mirror particles. Today's quantum bits are fragile, their coherence shattered by the slightest disturbance. But if qubits were paired with their inverted twins across the cosmic divide, errors in our universe might be automatically corrected by the mirror universe's opposing quantum state. It's like having a backup dancer who instinctively counters every misstep. Your performance stays flawless even if you stumble. Companies like IBM and Google are already racing to build error-resistant quantum systems. Could mirror matter be the missing ingredient? Transportation bends the mind even further. Wormholes, often dismissed as mathematically possible but physically impractical, might become stable if threaded with mirror matter. The exotic negative energy needed to keep a wormhole open could naturally exist in the mirrored cosmos, where gravity might repel rather than attract. Picture a subway system where stations exist in alternate realities. Step into a portal in New York and emerge in Tokyo seconds later, not by crossing space but by shortcutting through a higher dimensional mirror. The catch: any traveler would need to navigate inverted time, arriving before they left according to our clocks. Medicine might see the wildest transformations. In a mirror universe where entropy decreases, wounds heal spontaneously and aging runs backward. While we can't transplant entire organisms across realities, we might isolate biological processes influenced by mirror particles. Cancer cells, which thrive on disorder, could be neutralized by exposing them to mirror matter fields that reverse their chaotic growth. Imagine chemotherapy without side effects, tumors unraveling like knotted threads pulled from the wrong end. Even materials science would revolutionize. Room temperature superconductors, the holy grail of energy efficiency, might emerge from alloys blended with mirror atoms. In our world, electron collisions create resistance, but mirror electrons could glide frictionlessly through their counterparts, like two combs whose teeth slide perfectly without catching. Aerospace engineers could build alloys lighter than graphene yet stronger than diamond, woven from alternating layers of matter and its mirrored twin. The darkest application, weapons. A speck of mirror matter released in our universe would annihilate upon contact with regular atoms, releasing energy dwarfing nuclear bombs. Thankfully, containment is as implausible as the danger is extreme. Mirror matter's gravitational weirdness makes stable storage nearly impossible. but the mere possibility reminds us that every breakthrough carries shadows. The true power of these speculations isn't just their ingenuity, but their ability to stretch our imagination. By treating the mirror universe as more than a thought experiment, we force physics to confront questions that could birth entirely new fields. Whether any of these technologies ever materialize, they prove one thing: reality's boundaries are only as rigid as our willingness to question them. The concept of a mirrored reality has haunted human creativity for centuries, long before physicists put pen to paper to formalize the cosmic mirror theory. Ancient myths spoke of underworlds where time ran backward, while Renaissance painters hid inverted symbols in their works, suggesting hidden realms obeying different rules. But it was the birth of modern science fiction that truly unleashed this idea's potential. Take Lewis Carroll's Through the Looking Glass, where Alice steps into a world where memory works in reverse. She meets the White Queen, who famously claims to live backward in time, screaming in pain before pricking her finger. This wasn't just whimsy, it was an early literary experiment with the physics of time reversal, wrapped in the guise of a children's story. Cinema took the baton with films like Tenet, where Christopher Nolan weaponized inverted entropy, crafting jaw-dropping sequences where bullets flew back into guns and shattered glass reassembled itself. But the most profound explorations often come from quieter stories. Consider Counterclockwise, a 1960s avant-garde film that literally runs backward, transforming mundane activities into surreal poetry: a man uneating an apple, smoke retreating into a cigarette. These works don't just entertain, they rewire our brains to question time's arrow, making the unimaginable viscerally tangible. The mirror universe trope thrives because it subverts storytelling's most sacred rule: causality. Traditional narratives rely on chains of cause and effect, but mirrored tales force audiences to piece together plots where the climax might occur in the first act and the inciting incident in the last. Playwrights like Tom Stoppard Arcadia and novelists like Kurt Vonnegut's Slaughterhouse-Five have turned this into high art, crafting narratives where time is less a straight line and more a Möbius strip. Even comic books have embraced the idea. Marvel's mirror universe storylines explore worlds where heroes' moral alignments flip, suggesting that inverted physics might reshape ethics as radically as it does physics. Music, too, has danced with these concepts. The Beatles' Revolution 9 played backward sparked conspiracy theories about hidden messages, while avant-garde composers like John Cage wrote scores that could be performed in reverse. These experiments reveal a universal truth: reversing time doesn't just change the sequence of events, it transforms meaning itself. A love song played backward might sound like a funeral dirge. A whispered secret becomes a garbled omen. Perhaps the most fascinating cultural impact lies in how mirror universes reframe our anxieties. In an era of climate crisis and pandemics, stories like Twin Peaks, The Return or Dark offer catharsis by presenting worlds where entropy can be undone, where pollution might retreat into factory smokestacks, or viruses return to patient zero. These narratives aren't escapism, they're psychological rehearsals for a reality where science might one day bend time's rules. From Picasso's fractured portraits, which feel like glimpses of multidimensional perspectives, to the palindrome poems of the Oulipo movement, art continually circles back to the mirror universe as both muse and metaphor. These creations don't just reflect reality, they refract it, proving that the human imagination has always sensed there's more to existence than meets the eye or the clock. The cosmic mirror theory has sparked countless wild speculations, but not all of them stand up to scientific scrutiny. One persistent myth suggests that a mirror universe would be an exact duplicate of ours, with alternate versions of ourselves making opposite choices. While this makes for gripping sci-fi plots, the reality is far stranger. A true CPT mirrored universe wouldn't contain doppelgangers living backward lives. It would be a fundamental inversion of physical laws where particles spin counterclockwise, forces repel instead of attract, and time's arrow points the other way. The idea of mirror you sipping coffee as steam flows back into the cup is a poetic oversimplification. In reality, the mirror cosmos might not even support familiar chemistry, let alone humanoid life. Another common misconception conflates mirror universes with parallel worlds from multiverse theories. While both involve alternate realities, parallel universes branch unpredictably like tree limbs, each hosting variations of our timeline. The mirror universe isn't a random offshoot, it's a precise mathematical counterpart, bound to ours by CPT symmetry. Think of it like a vinyl record. Parallel universes are different songs scattered across the album, while the mirror universe is the same song played backward. This distinction matters because it changes how we search for evidence. We wouldn't look for historical divergences like dinosaurs surviving extinction. We'd hunt for anomalies in particle behavior or gravitational waves that betray an inverted reality's presence. Then there's the exaggerated claim that mirror matter could be harnessed as an unlimited energy source. While it's true that matter-antimatter annihilation releases immense energy, mirror matter isn't just antimatter, it's matter with inverted symmetry properties. The energy barrier between our worlds isn't a dam waiting to be breached. It's more like a one-way mirror, where any attempt to extract energy would likely disrupt the delicate quantum balance keeping both realities stable. Experiments like those at CERN have shown that even producing trace amounts of exotic particles requires colossal energy inputs, debunking fantasies of effortless cosmic power taps. Perhaps the most pervasive myth is that the mirror universe explains déjà vu or other psychic phenomena. While it's tempting to attribute uncanny experiences to glimpses of a backward-flowing reality, neuroscience offers clearer explanations rooted in memory processing and neural misfires. The mirror universe's timeline isn't a hidden layer occasionally bleeding into ours, it's a self-contained cosmos obeying its own physics. If any interaction exists, it would manifest in ultra-precise particle colliders, not in human intuition. The theory's mathematical elegance often gets overshadowed by these sensationalized versions. At its core, the cosmic mirror theory isn't about ghostly doubles or time loops. It's a rigorous framework exploring whether nature's deepest symmetries demand a counterpart to our existence. By stripping away the myths, we uncover a far more fascinating truth. The universe might be hiding its own reflection not for drama, but because that's how the math of reality balances itself. Every wild speculation debunked brings us closer to understanding what the theory actually promises and why that's astonishing enough without embellishment. The hunt for the mirror universe is shifting from theoretical equations to real-world experiments, with physicists designing increasingly ingenious ways to probe reality's hidden symmetries. One of the most promising frontiers is the next generation of particle colliders, like the proposed future circular collider at CERN. While current accelerators smash protons to study quantum fragments, these megaprojects could reach energies high enough to create particles that flicker between our universe and its mirrored counterpart. Imagine a detector catching glimpses of matter that seems to vanish mid-collision, not from technical glitches, but because it momentarily slipped across the cosmic divide. These elusive events wouldn't announce themselves with fanfare. Researchers will sift through mountains of data, searching for anomalies where energy or momentum doesn't quite balance, like finding footprints in snow that abruptly stop. Gravitational wave astronomy is another field poised to revolutionize the search. Upcoming observatories like the Laser Interferometer Space Antenna LISA will listen for ripples in space-time with unprecedented sensitivity. While LISA's primary goal is studying merging black holes, it might also catch whispers of mirror-matter interactions. Picture two black holes spiraling toward collision, except their gravitational waves carry faint secondary frequencies, as if something invisible is tugging at them from beyond our dimensional veil. These echoes could betray the gravitational influence of mirror galaxies, their mass-warping spacetime in ways ordinary matter can't explain. Then there's the cosmic microwave background CMB, the universe's baby photo. Telescopes like the Simons Observatory are mapping its faint temperature variations with microscopic precision. Hidden in these patterns might be the gravitational imprints of mirror galaxy clusters, subtle distortions where invisible mass bends the CMB's light. It would be like detecting a hidden mountain range by the way it distorts shadows on a foggy plain. Some theorists even suggest that certain large-scale anomalies in the CMB, like the infamous cold spot, could be bruises from a long-ago collision between our universe and a mirror domain. Quantum sensors are entering the fray too. Ultra-precise atomic clocks, like those being developed at the National Institute of Standards and Technology, could detect minute fluctuations in fundamental constants. If the strength of gravity or the fine structure constant varies inexplicably over time, it might signal our universe brushing against its mirror twin. These devices act like cosmic stethoscopes, listening for the heartbeat of a reality out of phase with our own. Perhaps the most daring experiments involve neutrinos, those ghostly particles that barely interact with matter. Projects like Dune Deep Underground Neutrino Experiment will fire neutrino beams through hundreds of miles of Earth, watching for particles that oscillate between known flavors and hypothetical sterile states. If sterile neutrinos exist, they might be messengers shuttling between realities, their odd behavior a cipher waiting to be decoded. The James Webb Space Telescope adds another tool to the kit. By studying the earliest galaxies, it could spot structures that formed too quickly to be explained by visible matter alone, hinting at mirror matter's gravitational scaffolding. Imagine finding a cosmic skyscraper where the blueprints only account for half the steel. The rest must be hidden behind walls we can't see. What unites these approaches is their reliance on asymmetry, the tiny cracks in reality's symmetry where mirror effects might peek through. Future breakthroughs won't come from a single eureka, a moment, but from patient accumulation of anomalies, each too faint to prove anything alone, but together weaving a tapestry of evidence. The mirror universe, if it exists, won't reveal itself in a flash of light, but in the quiet persistence of data points that refuse to fit our existing models. The coming decades will test whether this elegant theory can survive contact with observation, or if the mirror universe will remain one of physics' most beautiful might-have-beens. Either way, the search itself is reshaping our understanding of reality's deepest layers, proving that sometimes the most profound discoveries begin by asking what's hiding in the reflection. There's a reason the mirror universe concept grips our imagination so fiercely. It's the ultimate rebellion against the mundane. From childhood, we're taught that time flows forward, that cause precedes effect, that spilled milk never jumps back into the glass. These rules feel as fixed as gravity, yet the mere suggestion of a backward-flowing reality triggers a visceral thrill, like catching a glimpse of a hidden door in a familiar room. Psychologists call this cognitive dissonance, the exhilaration that comes when deeply held assumptions are appended. It's the same primal fascination that draws us to optical illusions, or M. See Escher's impossible staircases, where our brain struggles to reconcile conflicting realities. The mirror universe isn't just a scientific hypothesis. It's a mental playground where the ordinary becomes extraordinary. This allure transcends cultures and eras. Ancient Hindu cosmology spoke of cyclical time with alternating eras of creation and dissolution, while Norse mythology imagined Yggdrasil, the world tree connecting 9 realms with different temporal flows. Even modern blockbusters like Tenet or Doctor Strange tap into this timeless appeal, proving that inverted realities aren't niche ideas but universal curiosities. What unites these stories is their power to momentarily shatter our linear worldview, offering a taste of liberation from time's relentless march. For a brief moment, we're invited to imagine a life where mistakes unhappen, where aging reverses, where the future is as tangible as the past, a fantasy both exhilarating and unsettling. Scientists aren't immune to this pull. For physicists, the mirror universe represents more than just mental gymnastics. It's a stress test for our most fundamental theories. When a concept like CPT symmetry predicts that reality should balance on a cosmic scale, the absence of observable antimatter or dark matter's ghostly influence feels like a glaring loose end. The mirror universe offers an elegant solution, not by inventing new physics but by revealing hidden layers of existing laws. It's the difference between patching a leaky boat and discovering the boat was always meant to have a twin hull. This elegance, this sense of cosmic harmony, resonates deeply with researchers who spend their lives decoding nature's blueprints, but the fascination isn't purely intellectual. There's an emotional undercurrent to this theory, a whisper of existential comfort. If our universe has a mirrored counterpart, it means we're not alone in the most profound sense. Every supernova here might birth a star there. Every human thought here could ripple into an inverted consciousness elsewhere. This duality transforms the cold vastness of space into something resembling a cosmic companionship, a silent partner dancing to the same rhythm, just in reverse. In a culture increasingly aware of isolation from social fragmentation to the Fermi paradox's eerie silence, the mirror universe offers a poetic antidote, the idea that connection might not require proximity but symmetry. Yet the theory also unnerves us, and that tension is key to its grip. The possibility that our cherished sense of free will might be mirrored by predetermined choices in another reality strikes at the core of human identity. Are we captains of our fate, or merely one side of a coin mid-flip? This philosophical vertigo is why the mirror universe endures in pop culture, from Twin Peaks' cryptic doppelgangers to Black Mirror's tech-twisted reflections. These stories thrive because they articulate a fear as old as consciousness itself, that the self we know might not be the only version, that some unseen twin could be living our life backward, watching our end as their beginning. What's remarkable is how this idea bridges divides. You don't need a physics degree to feel the mirror universe's tug, just a pulse and a passing curiosity about life's big questions. It speaks to the scientist scrutinizing neutrino data and the teenager doodling time loops in their notebook. Few theories manage to be simultaneously so rigorously mathematical and so deeply human, so rooted in equations yet so ripe for metaphor. Whether it's ever proven or not, the mirror universe has already done something extraordinary. It's reminded us that reality, for all its apparent rigidity, might still have room for wonder. The cosmic mirror theory doesn't just challenge what we know, it redefines what we consider possible. Imagine standing between two mirrors, seeing reflections stretch into infinity, each one slightly altered, slightly reversed. That's the essence of this idea, a reality where time's arrow points backward, where black holes in our world might be white holes in another, and where every law of physics we take for granted flips on its head. This isn't just about solving cosmic puzzles like dark matter or the missing antimatter. It's about confronting the humbling truth that our universe might be just one half of a grander, stranger whole. What makes this theory so compelling isn't just its audacity, but its elegance. Nature loves symmetry, from the spiral of galaxies to the double helix of DNA. The mirror universe extends that principle to the fabric of existence itself, suggesting that the imbalances we've struggled to explain aren't flaws at all, but clues pointing to a hidden counterpart. Think of it like a sculptor chiseling away at a block of marble. What looks like chaos from one angle reveals a masterpiece when viewed from another. The cosmic mirror theory invites us to step back and see the bigger picture, where every unanswered question in physics might find its missing piece on the other side of reality. Yet for all its beauty, the theory remains tantalizingly out of reach. We're like detectives piecing together a crime scene where the suspect might be invisible, intangible, and moving backward through time. Every experiment, from particle colliders to gravitational wave detectors, is a search for fingerprints left by a universe that operates by inverted rules. The frustration is part of the thrill. Science thrives on the edge of the unknown, and the mirror universe represents one of the final frontiers. Not just a new place to explore, but a new way to see everything we thought we understood. And that's the real gift of this idea. Even if the mirror universe is never proven, the questions it forces us to ask are transformative. Why does time flow forward? What does it mean for something to be real? Are the laws of physics universal, or just local to our cosmic neighborhood? These aren't just academic musings, they're invitations to wonder, to marvel at the fact that we live in a reality where such questions can even be asked. The mirror universe isn't just a theory, it's a mirror held up to our own curiosity, reflecting back the boundless creativity of the human mind. So as we peer into the cosmos, let's not just look for answers. Let's look for the reflections we haven't noticed yet, the glimmers of possibility hiding in the data, the whispers of symmetry waiting to be heard. Whether the mirror universe is out there or not, the act of searching changes us. It reminds us that reality is far stranger, far more malleable than we ever dreamed. And perhaps in that strangeness, we'll find not just new physics, but a new way to see ourselves, not as solitary observers of the cosmos, but as participants in a story still being written forward and backward across the grandest scale imaginable.